Welcome to the office. We want to take a look at one of the big results of this section, in particular that the set of permutations with composition, so that binary structure, is indeed a group. All right, so these are one of our big theorems of this section. So let A be a non-empty set, and let S sub A, so this is new notation for us, let S sub A be the collection of all permutations of A. So S sub A is a collection of permutations. It is the things tau, that tau is a permutation of the elements of A. Okay, so it's a collection of functions. All right, S sub A is the collection of all permutations of A. Then S sub A is indeed a group under permutation multiplication. Excellent. If I wanted to verify this, now, the book gives a proof, okay? And their proof essentially is the same thing as what we're doing when we say verify it, right? Because a proof is a verification. But what we're doing here is we're just kind of omitting the structure as well as omitting some of the details. So that way we can work through it relatively quickly. If we return back to section 4 on groups here, I might say regarding the properties of groups, we have property G1. I think they use more of a cursive. So let's, I think that's what I did before. G1, there we go. All right, so group property 1 that must be satisfied is associativity. Are functions, or rather, is the operation composition commutative? Sorry, not commutative, associative. So is function composition associative? Yes. Function composition is associative. Wonderful. Are we going to show it? I'm not going to show it at this particular moment. The associativity of functions should be something that's established in a proofs course. If you're unsure of it, I would encourage you to take a look at some examples to convince yourself of the truth, and then see if you can write up a proof or a demonstration, right? A verification. Property 2, for a binary structure to be a group. Now we also require, let's see here, identity. So you want to verify that it has an identity. What we can do is we can take I, so it's a fancy I there. And now this is a little bit weird. We could say for the set A, there's element A1, A2, A3. And actually, you know what? Let's not write it in that way. That's how we've been writing our functions, but we can just use the identity function. I of A is equal to A for all A in A. Okay, excellent. If you wanted to write that in the same sort of notation that we have been doing, we could say that I is equal to for A1 and A2, A3, all the way up to A sub n for n elements in it. The image of A1 is A1, the image of A2 is A2, and the image of A3 is A3, and all the way up. Okay, so we have our normal representation of functions, the identity function. We also have the permutation representation. This is all fine. The thing that we have regarding our definition for permutations so far, we haven't actually required that A be finite. And if A is not finite, then we don't necessarily have this notation to use. So in theory, where we allow for infinite sets, this would be the better notation to use. Of course, when we are talking about finite sets, then we can work with this sort of a situation. Okay, and this is primarily what we'll be working with. All right. So the last property that we have to satisfy in order for a binary structure to be a group is inverses. So does an inverse exist? Yes, inverses exist. So let tau be a um, let tau be a permutation, right? That's what I want it to be here. If it's a permutation, tau is 1 to 1 and onto. So as a permutation, right, we're talking about it, we want to find an inverse for a permutation. But what we want to recognize is that tau is a function, and we already have good knowledge of functions. Tau is 1 to 1 and onto. Therefore, tau inverse exists, right? As a function that is 1 to 1 and onto, it has an inverse function, and tau inverse is 1 to 1 and onto. Therefore, it is a permutation. That is, inverses exists. The inverse of tau exists. And of course, we denote it as the usual notation, tau inverse. So because of our knowledge of functions, we know that this group is associative. We know that there's an identity, and we know that there are inverses, okay? Because we have a familiarity with functions. Since we're looking at this new context, it seems a little bit weird, but again, sitting in this new context, focus on the things that we already know. We already know a fair bit about functions and function composition. All right, the last thing that I wanted to give here is just another notation. So if A is the finite set 1 through n, then the frup, also known as the group, silly me, the group of all permutations of A is the symmetric group on n letters and is denoted by Sn. Okay, so here they're using the word letters even though it's numbers. Why do they do that? I don't know. We oftentimes will permute letters. If you take a discrete math class, they'll look at that sort of a thing. How many permutations are there in the letters? How many permutations are there of the letters in the word Mississippi, for example? Okay, it gets more interesting when the letters are non-distinct. Anyway, so it's often permutations on letters. I'm not sure why they're using that here because we're using numbers as the elements of the group or of the set, and then we're looking at the group of permutations. All right, that's all that I wanted to share for now. What we'd like to do beyond this is actually look at some examples that we're going to consider in class. So we'll look at one more theorem that's just a simple statement of the theorem itself, and then we'll call it good for this section. So join me in the office for one more video.